So this, the output current of this, if I plot I out versus the input differential voltage, what does that look like? What will be the curve? It will have a slope of GM1 at the origin, and then it compresses, and at some point it becomes flat, and the flattened value is I naught. Okay, that is the tail current, isn't it? Now, if you connect up this transconductance as a unity gain voltage follower with a certain load capacitance CL, okay, let's say it is initially biased at this point, that is, you have let it reach steady state with a certain input bias, okay. The input voltage is like this. This is the increment around V bias. Okay. Let's say V bias plus V in. What I am plotting here is just V in. And the output also will be 0. Okay. 0 increment around its bias point. If I apply a small step, what happens? The output will, if the step is small, by small I mean, let's say it's confined to this region, maybe this is the step, okay, then you can assume the characteristics to be somewhat linear, and the output will rise up like an exponential, and the time constant of the exponential is 1 over omega u, or CL by GM1, okay. This is the time constant. Now, if we modeled an op-amp using its unity gain frequency, this is what we expect. And from this we can calculate the settling time for any accuracy, okay, if the op-amp were linear. Now, what happens is, if I apply a large step, okay, I will apply a step. So, initially it is at this point here, and the step input takes it to some point here, okay. So, output voltage does not change suddenly, it cannot, because of the capacitor. So, the differential pair is operating with an input voltage which is equal to this much, okay. So, the transconductance behaves like a constant current source of value I naught, which will charge up the capacitor. This is okay. This is called slewing. This is the maximum rate of change, although this voltage may be within the swing limit of the op-amp, okay. What is this value? What is the voltage at which it enters, it becomes flat? It's square root 2 times the quiescent VD sat of M1 and M2, okay. And if we choose VD sat 1 to be, let's say, 150 millivolts, how much is that? That's about 200, 220 millivolts or so. So, clearly that can be within the swing limits of the op-amp, but it will not follow 1 minus e to the minus omega ut, okay. It's hard to calculate in general what happens, but first we can assume a fictitious characteristic like this. It has a slope and it's perfectly linear up to the saturation values. Let's say this is I out versus VD of the differential pair. We know that our characteristics are not like this, but let's assume for the moment that they are something of this sort. Okay. The real characteristics are that it has this slope, and the slope goes on reducing, and at some point it saturates. Okay. If I assume the black line to represent the characteristics of the differential pair, what happens when it slews? I still use the voltage follower with a capacitive load. In response to a step, I will assume that the step is large, perhaps this much. Okay. This is Vp, this is Vp, so it will slew. So if you plot V out, it will start ramping up at a rate. What's the rate of ramp up? I naught by CL. Okay, then what happens? The output voltage will keep ramping up. That means that this is the input step that is applied. As the output keeps ramping up, the differential voltage across the differential pair keeps on falling. Okay, this is fixed at Vp, this is ramping up, so this keeps falling. Once this falls to this particular value, let me call it Vmax, that is the limit for slewing. Okay, once it falls here, then the output current is proportional to the difference voltage of the differential pair. Okay, so from that point onwards, it will follow this exponential. Of course, it will have some initial condition, which is Vmax, and then it has a time constant 1 over omega u. Okay, so that's what happens with slewing. So you know that if you start a first order system with an initial condition and it has a final steady state value, the initial condition will decay as e to the minus omega ut and the final value will rise up as 1 minus e to the minus omega ut. So that's what I have written here. Vmax is the initial condition for this differential equation. Okay. Now if we didn't have slew limitation, that is if we had characteristics like this, what would happen? The current at the start of the process will be larger, which means the slope will be larger. It would have done something like this. Okay. So when you have slewing, the settling time is longer for any settling error. Okay. So when you calculate settling errors, you also need to take into account this factor, and this is why slew rate is important also. So if you are operating with small signals, you can calculate the settling behavior using the linear equivalent circuit, and you adjust the unity gain frequency to be some particular value. Okay, but it's not enough if you do that. When you have large steps, you have to make sure that the slew rate is sufficiently high, or you have to take into account the slew rate and your settling time specification should be large. Okay, so settling time includes slewing time, and this part is known as linear settling because it follows a linear differential equation. Once it comes into this region, okay, the linear region. So I assume that my transconductance is like this. It is piecewise linear. It is linear around the origin, and at some point it saturates. Okay, and this is what is in this part. So up to plus minus Vmax, it behaves linearly. Okay, so I start from a particular Vp, and the output starts ramping up. When the output ramps up to Vp minus Vmax, the input differential voltage is within this range. Is that okay? This is fixed at Vp, okay, and the output was 0, and it will start ramping up. When it reaches Vp minus Vmax, the input differential voltage is Vmax, okay. After that, it follows the linear settling. This was in error. This initial condition is not Vmax for the output, it is Vp minus Vmax, okay. Is this okay? Any questions on when it slews or the analysis? So the bottom line is some part of time for which it slews, and after that it settles linearly when the input differential voltage becomes very small. This is again true of all op amps. And the slewing limit generally comes from some current limitation. Okay. because all of our circuits are voltage controlled current sources which are driven into capacitors, resistors, some impedances. Now the voltage controlled current sources don't behave linearly for very large inputs. The output current gets limited to some value. Because of that, if that current is going through some capacitor, the rate of change of voltage can be limited. So there is a dynamic large signal limitation which is the slew rate. Okay. The question was how one gets the sum of exponentials for linear settling. If you have a first order system, something like this. Okay. Now, let's say u is a unit step, that is a piecewise constant. I mean, in general, u can be a function of time, but I am assuming it's a piecewise constant. So, u is 0 for t less than 0 and u is some Vp for t greater than 0, let's say. At t equal to infinity, this is the steady state, right? So, x equals Vp. And at t equal to 0, so let's say x is some initial condition. The solution to this type of equation is v of 0 e to the minus omega ut plus v of infinity 1 minus e to the minus omega ut. Is this correct? Is this correct or no? It is correct, I think. Okay. Yeah. So it has a time constant e to the minus omega ut. I think if you go back to your basic networks, you will see this. But even if you solve it exactly, you will see this one. I think this is correct. Okay. Is that okay, or does it need more explanation? So, and you can see the sanity check. When t equal to 0, this part is 0. When t equals infinity, this part is 0. So it goes from v of 0 to v of infinity, and there is one time constant associated with the whole process. Now the reality is slightly more complicated than this because the slope changes continuously. Okay. So what happens is that it comes out of slewing, but it doesn't start, I mean it's not exactly linear settling. Okay. Because this again is still a nonlinear settling because the slope itself is changing. It is not slewing anymore, but the slope is dependent on the input voltage. So it will take some time. I mean, you can try to solve the nonlinear differential equation or you simulate it. Okay. Is it okay? So is the settling going to be faster or slower? So let's say I have three cases. One is a voltage controlled current source with no limitation. Okay. This is I out versus Vd of my differential pair. So this is the extreme ideal case where I don't have any limitation at all. The slope of this is Gm 1. Okay. The second case is it follows the straight line for some time and then at plus minus I naught it saturates. And finally the last case is the slope gradually decreases and at a later point it saturates. Okay. So this is linear but with slew limit, and this is the actual differential pairs characteristic. Now we already discussed several times with the linear characteristic without any limitation, the output will be something like this. Okay. The input step is Vp, the equation followed will be Vp 1 minus e to the minus omega ut. I am assuming zero initial condition around the bias. So what will happen in the other two cases? Will it settle faster or slower? Slower. So which will be slower? The linear with slew limit or the actual one? Why? Why is it slower? You have to charge the capacitor to a certain voltage Vp finally. Okay, so you have to deliver an amount of charge CL times Vp. Okay, and what is charge? Integral of current over time. Now the actual curve delivers less current for all values. Okay, so it takes more time. The exact curve is not important, but the fact that it is lesser than the linear width slew limit for all values of Vd means that it will take more time. Okay. So the linear one may do something of this sort. There is a clear demarcation between slewing and linear settling, because this limit occurs at a higher value of Vd, it slews for a shorter time. Okay. So this value we said was root 2 Vd sat 1. Okay. What will be this value? If I made an idealized differential pair like this, what is this value? Vd sat 1 by 2. Right? It is I naught by Gm, of course, which happens to be Vd sat 1 by 2 in this case. So it will slew for a shorter time, but after that it settles slower. Okay. So it may do something of this sort. Is this clear? So slewing is important for this, because if you only calculate the settling time from the linear differential equation, you will be wrong, meaning it's going to take longer time to settle. So you have to account for slewing also when you are dealing with large signals. Any questions on this? This is the last of the specification that we had to discuss about the differential pair. Any questions on the differential pair? The question was, are the positive and negative slew rates always equal? Isn't it? Yeah. So the answer is that no, they are not equal in general. In this case, they happen to be equal. I didn't hear the question. For small steps, the two are equivalent, the three are equivalent in this case. Okay. This is the system without slewing. It has a slope of Gm1. This, the red one is the system with slewing, but it has a piecewise linear characteristic. And this thick blue one is the actual one. Okay. So all of them have the same slope. So if you apply a small step, very small step around the origin, then they will all settle equally fast or equally slowly. Okay. And that settling time is related to the slope, Gm1 by Cl. That's the inverse of the time constant. Now if you have slewing, then it will settle slower than that. Okay. Because you can clearly see the current delivered by the red curve here is lower always than the black curve. It's either lower or equal. Similarly, the current delivered by this actual curve is lesser than the red curve and the black curve for all values of input. So it's just going to take more time to charge up to a given value. Okay. Now because the slopes are equal at the origin, if you are dealing with very small steps, they all take about the same time. Okay. So slew rate is the fastest that a system can charge, right? It's the fastest that a system can rise, but that doesn't mean for fast settling you should have slewing. Is this clear? So in fact it's an upper limitation. With the linear characteristic you would have wanted the voltage to rise up faster, but with slewing it is not able to do that. The question is, how do you measure the slew rate? So you will apply larger and larger steps and find the rate of change of the output. So what we'll do now is to go back to a couple of questions from the last assignment. So one of the questions was to find out Vx when the resistances are different. Okay. This is just analysis. There is no big deal in the analysis. You write the Kirchhoff's current law at this node, and this node. So you get these three equations and then you solve for Vx. So what is the conclusion? So when R1 equals R2, it's clearly 0. This we know from symmetry and differential equivalent circuit and all of this stuff. Is there any other condition? GDS equals 0. That is for sure. Yeah. If GDS is 0, again Vx is always exactly equal to 0. So there is a third case where R1 and R2 are different maybe, but both of them are very small compared to RDS. Then also it is 0. So the equation, the result looks like this. Okay. After you rearrange the terms and so on. So you can see the numerator is GDS by G2 plus GDS minus GDS by G1 plus GDS. Did you get something of this sort? Clearly, if G2 is G1, then the numerator goes to 0. Okay. And if GDS itself is 0, also it goes to 0. Now the denominator is 2 plus some other numbers. Okay. Here you have 2 and all the other numbers are of the form GDS by GM, which you expect to be smaller than 1 anyway, right? So this also, you have GDS by G2 plus GDS and so on, some other things. So roughly speaking, the denominator doesn't change too much with the relative value of GDS. Okay, except of course if GDS is 0, it's a different thing. Now the numerator has GDS by G2 plus GDS. So if G2 is much more than GDS, then the absolute value of the numerator becomes small, even if G1 is different from G2. Is it okay? So the two conditions, the first two are obvious. G1 equals G2, this is symmetry, and then GDS equal to 0. Then what happens is really that if GDS is 0, these two are ideal current sources. Okay. So what happens on top doesn't affect what happens here. It will pump an ideal amount of current. That's why you get 0. Okay. Then finally, if G2 and G1 are much greater than GDS, then Vx is approximately 0, because the magnitude of the numerator becomes very small, whereas the magnitude of the denominator is close to 2. Is this okay? So what's the point of this? So what I did was, in most of my analysis, in all of my analysis in fact, I terminated this with a voltage source. Okay. So what is G1 and G2 in that case? What is G1 looking in here? Or G1 is GMP. And what is G2? Infinity. Okay. I mean, the conductance is infinity, the resistance is 0. So this is why I did it like this. If I did analysis, tried to calculate the voltage gain this way, it would have been a bit more complicated. Of course, you should get the same answer, but is it okay? So when I short circuit the output, then I can assume this voltage to be 0. When I open circuit it, I cannot assume that. We will continue to do this in the later stuff also, okay, when we have more complicated GMs. Any questions on this? So there's no big deal in the analysis. It's just a matter of putting the 3 equations and getting the answer. But you put it in this form or maybe a couple of other forms, it's convenient to interpret. And this is the interpretation. Okay. These two I think you already knew. This is something that I used while doing the analysis. This is okay? So if that is okay, then let's move on to the next one. I'm not going to discuss all problems today, only some that are relevant to what we want to do next. You have I naught and ideal sources, okay. And you are asked to calculate the differential gain, okay. V out, and then you have an increment Vd by 2 and minus Vd by 2 here, around some common mode of course. And the other circuit, and you are asked to calculate the voltage with respect to ground. So what's the answer? Why? What happens if I replace these current sources with resistors of R? What gain do you expect here? In this case, this is Gm by GDS, and here also it is Gm by GDS. Whatever it is, it's equal in the two cases. Now, if I replace the current sources by resistors, do you expect the same thing? What do you expect? Half. You get half the gain in the second case than in the first case. So why is it the same here? Actually what happens is, here this is an ideal source of I naught, okay, and this is also an ideal source of I naught, okay, and if you look at this branch current, it is always I naught by 2. The incremental current here is 0. When we have an incremental voltage of 0, we replace it by a short circuit. When we have an incremental current of 0, we replace it with an open circuit. Okay? So the small signal equivalents of the two circuits are the same, exactly. Is this okay? If I open circuit this one, let me write the small signal equivalents. The first one is pretty clear. And this is an open circuit, this is an open circuit, and this is an open circuit. Okay? And you are asked to calculate, let me call this D1 and D2, the two drains. You are asked to calculate the difference between the drain voltages. In the other case, the equivalent circuit looks like this. This is an open because it's a current source, and this side also it is open. Okay. Now this is connected to ground, and you are measuring the voltage between this point and ground. Okay. So you really are measuring the voltage between these 2 points, between the two drains. Okay, and the incremental current here is 0. So you get exactly the same answer in the two cases. This is more of a puzzle-like thing. This is not all that useful for circuit design. Okay, let's move on to one more problem which I wanted to discuss. This is the cascode. I won't discuss the whole problem now, but only one part of it. So this is at some V bias 2, let's say. Now I said that the reference branch has n times smaller current. Okay, I want to get a current source of I naught. Now I can have any current here and multiply it by the appropriate value. Okay, so each of this is W2 by N by L2, and this is W4 by N by L2. Okay, so what are the small signal parameters of M1 and M3? So let's say this is GM4 and GDS4. What are the small signal parameters? This will be GM2 by N and GDS2 by N also. Okay. So everything is n times smaller. It is like taking one nth, you cutting up into n slices and taking one of those slices. So we can discuss this in detail later, but what is the output noise? So let me take a simple current mirror. Again I do this. This is I naught. This is I naught by N. This is W by L. This is W by N divided by L. Okay. First of all, what's the motivation to do this? The current source is what I am really interested in. This reference branch is extra. I don't want to spend too much current in that. So I will reduce the current and scale it appropriately. Okay. That's the main motivation for doing this. And this is very common. The reference branch currents are smaller than the main current. Now, what is the output noise you see here? Let's say this was biased with an ideal voltage source. of the appropriate value. What will be the output noise current? M2, M1. What is the output noise current? Yeah, what is it? 8/3 kT GM2. Okay. Now, if I bias it from this source, what is the noise current? You will get okay. This is from M2 and this is from M1. So this is the disadvantage. You will get a larger noise if you try to reduce the reference branch current, because its noise will get multiplied by a factor of n square. What is the noise current spectral density of M1? Huh? Yeah, if this is GM2, this is GM2 by N. So the spectral density is 8/3 kT GM2 by N. But it's a mirror of ratio N. So this gets multiplied by N square. Okay. So there are cases in which you don't want to do this. You will in fact have to use the same current, and in some extreme cases even more current in the reference branch than in the main branch. There are practical cases where this is necessary. So when the noise of the current source influences the noise of your circuit significantly, you don't want to do this. So one example is voltage controlled oscillators. The voltage controlled oscillator is biased from this current source. It turns out that it can be very sensitive to the noise here. Okay. So there certainly you don't want to multiply up a very small current. You will have to go from a significantly large current to whatever you have. This is okay. So that's one part I wanted to discuss here. So a very large capacitor here, it will filter out the noise, it will reduce the noise spectral density, but the size of the capacitance can be very large. Okay, that again depends on the frequencies of interest. So you do that also, but even then, over some frequencies, at DC this has no effect. So the low frequency spectral density will still get multiplied. So depending on the frequency of interest, you may be able to do this. So the reason I brought this up was, that's how we bias everything, including our differential pair. So this is what it will be. Okay, we have the differential pair op-amp and then some reference branch biasing it, and you typically make the reference branch current very small because you don't want to waste current. So is there any penalty that you pay in this case? Noise. Why? In this particular case, the noise from the current source doesn't appear at the output when it is biased in the quiescent condition. So it doesn't matter. In fact, you do bias it at a smaller current. That's why the assignment asks you to do it at 1/10. So with the information that we have, you should be able to design the differential pair op-amp. Okay. The rest of the cascode versions are not really designs to some specification. What I've asked you to do is to simply modify the differential pair. We'll discuss that also on Monday, but it's not a new design. Okay. So it should take you a very short time, but you can spend maybe this weekend or a couple of days on designing this op-amp properly. Okay. And this is the data sheet of the op-amp. Now, of course, it's not in terms of particular numbers for a design that has already been done, but in terms of general quantities. Okay. All of the stuff we know. The transconductance is GM1, the gain is GM1 by GDS1 plus GDS3. Now, one of the important things that I didn't discuss, but which is pretty obvious, is the input capacitance. That is CGS1 by 2. The differential input capacitance. You have two capacitors in series. From between here and here, you have CGS of M1 and CGS of M2. Okay. So the differential capacitance is CGS1 by 2. Why is that important? Have you seen any case where it is important? Now, have you seen a case where the input capacitance of an op-amp is important? We have seen it several times. If you have an amplifier with a resistance and feedback, and you have something like this, what will this do? What does this do? Ringing. So it introduces additional pole in the feedback path, and you can have ringing and instability. So that's why that's also important. And then omega U is GM1 by CL, and there is a pole and a 0, additional pole and 0. The input referred noise spectral density is basically because of GM1, and there is some additional component because of the current mirror load. Similarly for the offset, here I have ignored the current factor error, I have only taken the delta VT, okay. And the common mode voltage and V out have some ranges. This is the slew rate, and the supply current is I0 plus IREF. It's to reduce this that you would want to minimize IREF. Now, of course, it's one thing to go and start from a spec and try and design all of these things. Sometimes you may not have this many variables. You can't put all of this and then get the right values and come up with a design. So the more important thing, like you should have a better understanding to modify your op-amp in a particular way. Okay. So let's say you design an op-amp and it has a unity gain frequency that's smaller than what you need. What are you going to do? Increase GM1. That's the only thing you can do. So how will you do that? Two alternatives: pump in more current or increase the size of the transistors. What's the trade-off associated with these things? What happens if you pump in more current? Is there any disadvantage? Power dissipation will go up. Anything else? Swing will also reduce because this VD-SAT terms will increase. Okay. So if you just increase the current in the op-amp, the unity gain frequency no doubt increases, but the swing limit will reduce. Okay. And the power dissipation increases directly. So let's do the other thing. Let's increase the size. What happens then? So the input capacitance increases. The parasitic capacitance is everywhere increase. So the pole and zero also move to a lower frequency. So that's the trade-off. So let's say your input referred offset is too much. What will you do? Increase GM1. What will you do to reduce the input referred offset? So you can reduce GM3. So what will happen in that case? So if you reduce GM3 for the same current, you are operating at a higher VGS minus VT. So again the swing will reduce. If you increase GM1, what happens? First of all, now you are messing around with too many other things. If you increase GM1, your unity gain frequency will increase. That may or may not be desirable. Okay. So you will try to reduce GM3, or what else can you do if you don't want to do either of these things? You want to keep swing limits the same, everything else the same. What are you going to do? Increase W by L. If you increase W and L both by the same factor, the offset will reduce because you increase the area. Okay, you increase the area of all transistors while keeping WL by L the same, you will improve the offset. So what's the disadvantage here? Parasitic capacitance. So the point is that everything is associated with a trade-off. Okay. Now I want to get the same op-amp, same unity gain frequency, but with a smaller current consumption. What will I do? I want to reduce the power dissipation in the system. How will I do that? Obviously, that's a very important goal. The whole thing, idea is to design everything at low power. Scale down the W by L. No, I want the same unity gain frequency. I want the same op-amp but a lower current consumption. What will I do? And so I'll reduce I and increase the W by L. Basically, I'll reduce I and reduce VGS minus VT. Okay. Can I keep on doing this indefinitely? Can I get the same op-amp at almost zero current? The capacitance will dominate, but even more than that, can I keep doing it even if capacitance is not important? So what happens in subthreshold? What's the problem with subthreshold? There is no problem with subthreshold, right? Huh? No, let's say the speed is not important. Maybe I had a slow op-amp to start with. GM reduces. Why? No, in subthreshold, the GM is independent of the aspect ratio, right? That's why you can't do this. It's dependent only on the current. It's only in strong inversion region that you can reduce current, increase the aspect ratio and get the same GM. Whereas in subthreshold, you can't do it. whatever you do to the aspect ratio, it will not change the GM. It's only dependent on the bias current, like a bipolar transistor. So, once it goes into subthreshold region, you can't reduce the current anymore without reducing GM. Okay, that's the main point. Now, the other point is also that, of course, the parasitics have increased and it may affect you. Maybe it will form a dominant part of the load. But even if that's not the case, you can't do this indefinitely. You will reach a limit where you have to burn a certain current, and that current equals the GM times some VT. You can work out the other trade-offs, but the bottom line is if you try to increase any one of them, you will have an effect on the other ones, and you have to find a sweet spot where it's best, meaning it uses the lowest amount of power, but of course it uses enough power to get you the job done. Okay. So you can work it out for the design. It's a pretty simple design, so you should be able to get it done.